Here's kind of an interesting scheduling problem where the variables are a little less intuitive or a little less obvious. So you have a hospital and they're making a weekly shift schedule for their nurses. And I've got this chart here that shows how many nurses are needed on each day. So Sunday you need 125 people, Monday 95, and so on and so forth. So we'll have a constraint that says each nurse works 5 days in a row because you don't want to have weird shifts where the nurses, work 2 days on and then have a rest and 3 days on or something like that. So we'll say the nurses have to work in a consecutive block. And what do we want to do as a hospital? Well, we'd like to minimize the number of nurses that we have to hire while still meeting all of the demand. So you'll notice in this problem, integrality is actually pretty important in the sense that you can't have half of a nurse, right? Well, you could, that would be like a part-time employee or something like that, but we're going to set that issue aside for now. I will mention also that you could probably reason out that even if you do solve the linear problem and you have a fractional solution, that the error that you're going to get is bounded by at most 7, and that would be a good topic for discussion here. Where did that number come from? Anyway, that's the problem. You have a certain each day of the week you have a certain number of nurses that you need to have available at the hospital. They work in shifts of 5 days, and so we want to figure out how many nurses we should hire, on what days they should be hired, in order to satisfy all of our demand, but minimizing the total number of nurses, which presumably has to do with cutting costs. So a false start for this problem, or a bad attempt, but also the most natural thing that most people do, is they say, well, we'll let xi be the number of nurses that are working on day number I. And then therefore, if those are our variables, then we'd say, okay, x1 for Sunday is at least 125, x2 for Monday is at least 95, and so on and so forth. That isn't a good formulation because it doesn't make there isn't a natural, obvious way to enforce this constraint that the nurses have to work 5 days in a row, right? It's not easy to see how you would do that. And so the way that you would remedy that, it would be a good idea to think about this to yourself before we go through the answer. But the answer is what's written right here. What you want to do is you'd let xi be the number of nurses who start their shift on day I. So that's going to be our variable. Xi will be the number of nurses who start their shift on day I. And now let's look at the linear program that comes from this. So our goal is here, what are we going to look at here? It's a minimization problem because you're minimizing the number of nurses. And you'd say every nurse that you hire starts on one of the 7 days of the week. And so your objective function is just the sum of these x's here. This is the sum of all the nurses who start on day 1 plus all the nurses that start on day 2 and so on and so forth up to all the nurses who start on day 7. That, not surprisingly, is the total number of nurses that you are going to hire. So what do the constraints look like? Why is it that this formulation makes it easier to represent this condition that you have the right number of nurses for each day? Well, if you look at the constraints that I've written here, you'll see I've got 7 constraints, one for each day. So I had 125 nurses needed on Sunday, 95 needed on Monday, 110 on Tuesday, and so on and so forth. And so let's look at what these constraints say. Let's ask this question. If we decide that x sub I is the number of nurses who start their shift on day I, then let's ask the following question. Let's say, which nurses are available to me on Monday? On Sunday rather, which is the first day of the week. Well, the nurses that began on Sunday certainly will be there. They've just started their shift. Nurses who started on Saturday, that's x sub 7 because Saturday is the 7th day of the week. Nurses who started on Saturday will still be there because they just started their shift the day before, as will nurses who started on Friday or Thursday or Wednesday. But the nurses that are not present, which are not showing up here, are those nurses who start their shifts on Monday or Tuesday. And the same pattern happens if you go down the line here too. So this is Sunday, Monday, Tuesday, Wednesday. Thursday gets 100, right? You'd say, well, which nurses are going to be there by the time Thursday rolls around? Well, certainly the nurses who started on Thursday, they're just showing up. And then there's also the nurses who started on Wednesday and Tuesday and Monday and Sunday. So the ones that excluded are Friday and Saturday nurses. Okay, so those are your constraints. You have these sums have to be greater than or equal to the right-hand side vector here, because you have to have at least this many nurses. You could have more, right? Maybe it works out in such a way that there isn't a way of getting exactly the right demand, that you have to have some extra at some point. But you have to have at least that many nurses. So that's why we have greater than or equal to signs here. And then other than that, the only other constraint is non-negativity, right? You can't have a negative nurse. I guess that would be a really unproductive nurse or something like that. But for modeling's sake, we'll assume that you don't have that. So that's a scheduling problem. Transportation, the transportation problem. I have it written here in text in the slides up there, but what I'd like to do instead is explain this with some pictures. In fact, I won't even use this one. I'll use a very simple picture here. In this diagram, we've got two things going on. We've got some warehouses. We've got two warehouses, and they are shipping things off to these stores over there. And I have some text annotating this. So warehouse number 1 has 60 units of some product available. So we'll assume there's just one product that these warehouses and stores exist to sell. The first warehouse has 60 units of the product. The second one has 40. The first store has a need. The first store needs 30 units of the product, which will come from these warehouses. The second store needs 40 units of the product, which will also come from these warehouses. And the third store needs 30 units of the product, which will come from these warehouses. You'll notice that I've set things up. Let me clear things up a bit. You'll notice I've set things up a way that the amount of the product that the warehouses have, the total amount of the product that they have, is 60 plus 40, which is 100. So collectively between these two warehouses, there are 100 units of the product. And collectively among these stores, the amount of demand is exactly 100 as well, 30, 40, 30. So supply, in a sense, matches the demand. So what are we doing here in this problem? I've got stores that need things, and I've got warehouses that have things. And so the goal here is that I want the warehouses to send things to the stores, and I want them to do so in a way that is as cheap as possible. You'll notice I've got these numbers here, $5 per unit, $12 per unit, $4 per unit. Okay, what does that represent? What those numbers represent are the following. Let's suppose that warehouse 1 decides to send, let's say, if warehouse 1 decides to send 30 units of the product to store number 1. So then how much do we pay for that? There's 30 units of the product going from warehouse 1 into store 1, and that costs us 30 times $5 per unit here, which is $150. Okay, on the other hand, if we were to send, say, 15 units from warehouse 1 and 15 units from warehouse 2, then the amount you would pay would be 15 times $5 plus 15 times $12, which is $255. So the question asks, what is the best way that you can, or the cheapest way that you can send all of the units of the product on the left to those stores on the right? I'm going to skip to the solution just to show you a picture, and then we'll talk about the formulation. Here's the solution right there. The solution looks like the following. Warehouse 1 sends 30 units of the product, just as we said a moment ago, into store number 1. And then it sends another 30 units of the product into store number 2. Okay, at that point, store number 2 has received 30 units from warehouse 1, and it needs another 10 because it needs a total of 40. So warehouse 2 sends 10 units to store 2, and then warehouse 2 sends its remaining 30 units over to store 3. And if you add these numbers up, if you add 30 times 5 plus 30 times 4, and so on and so forth, you'll see the optimal cost turns out to be 430. Okay, that's fine. So that's the answer, and I'm showing you that just so you have a sense of what is under your control and what isn't. So let's bring up this formulation again. Good idea here is to say, well, this is a minimization problem. Our objective function is we're minimizing the cost of transporting all this stuff from the left side of the screen to the right side of the screen. How many variables are there? That's an important question. You should pause and think about that for a minute, or we'll have a discussion on this. How many variables are there in this problem? There are 6 variables in this problem. 6 because that's 2 warehouses times 3 stores. You have a variable for every warehouse and every store. You have a variable indicating how much stuff you send from that warehouse to that store. So you'd have a variable from 1 to 1. You'd have a variable from, I'll draw them here again. You have a variable for how much stuff goes from 1 to 1, how much stuff goes from 1 to 2, how much stuff goes from 1 to 3, and then you have a variable for how much stuff goes from 2 to 1, and 2 to 2, and 2 to 3. So you have 6 variables altogether. Now, that means that your linear program, we can write the objective function first, then we'll look at the constraints. So my objective function looks like this. I'll say you now have, whereas in the previous problems we had, x1, x2, x3, x4, now we have a matrix variable, right? We have xij represents how much stuff goes from warehouse I to store j. So I've written my variable here as being a matrix, and that's just because that's a convenient way to represent it as a 2 by 3 grid or a 2 by 3 matrix, because you have 2 warehouses and 3 stores. Now, a lot of people ask at this point, how do you know you can do that, right? How do you know that you can suddenly go from vectors to matrices? The answer is, well, you could call these variables anything you like, right? I could have called these x1 through x6, and I could have just remembered that x1 is warehouse 1 to store 1, and x2 is warehouse 1 to store 2, or had some kind of encoding for that. I could have called them xa through xf. I could have called them x smiley face through x treble clef through x peace sign. I could have any name I like, right? The names or the indices don't actually affect the problem itself. I happen to choose this way of writing them out because it's convenient for me and it's intuitive, I think, in terms of teaching. You will often see in research that you won't just see xij even. I've seen research papers that have a whole lot of superscripts and subscripts, and in fact, optimizers love this kind of thing. I have seen things of the form, if this will show up here on my whiteboard, which is a little sluggish. Yes, there's an X. I've seen X, I, J, K, and then a P and a Q up there, and then an R was in a reverse subscript like that. That was in a paper that I reviewed quite a while ago. These were all, this was in effect a 6-dimensional array. And it was something like this variable represents the amount of stuff that goes from I to j at time k using vehicle P, which is piloted by driver Q, who's coming from a rest stop at R or something like that. These optimizers, operations researchers, linear programming people love their superscripts and subscripts. You get very used to seeing that, and it gets to be kind of a nuisance, but also kind of amazing. Getting back to the problem at hand, let's look at the objective function. So what have I done here? I have 5, let me erase that little circle I drew. I have 5x11 plus 4x12 plus 6x13. Where did those numbers 5, 4, and 6 come from? The 5, 4, and 6 that I just wrote come from this 5 here, and this 4 here, and this 6 down here. This is how much, $5 per unit is how much it costs to go to store 1, $4 to go to store 2, and 6 to go to store 3 from warehouse 1. So it's $5 for every unit that we send from warehouse 1 to store 1, $4 per every unit that we send from warehouse 1 to store 2, and $6 for every unit that we send from warehouse 1 to store 3. Similarly, the 12, 7, and 3 coefficients over here come from the, and let's kill this once again, like that, come from the costs that are coming out of warehouse 2. So that's 12 and 7 and 3 like that. So this objective function here is the total cost of all of the stuff that I am sending along transportation, all the stuff that's being transported. Okay, so you want to minimize that, minimize the total cost of sending things along. What are my constraints here? Let's look at these. We're going to divide these things up because I want to point out that the first 2 constraints are different from the last three constraints, and then of course you have non-negativity at the end. You can't send stuff back in the other direction, or you can't have these values be negative. That would mean stores are sending things back to the warehouse and they're getting paid for doing so, which makes no sense. So let's look at this one here. Let's look at the top two constraints. So this one says 1, 1 plus 1, 2 plus 1, 3 is 60. What is 1, 1 plus 1, 2 plus 1, 3? X1, 1 plus X1, 2 plus X1, 3. That is, I'll draw that out in this diagram here. X1, 1 is all this stuff. X1, 2 is all this stuff. And X1, 3 is all this stuff. And the constraint says that has to sum to 60. And where does 60 appear in this picture? Well, it's right over there. I just erased it for no particular reason. It's this thing. Okay, what does this say? This says X11 plus X12 plus X13, this thing here, that is just all the stuff that is leaving warehouse 1. It's all the stuff that is going from warehouse 1 either to store 1 or store 2 or store 3. And I've said that has to be equal to 60. Now, what does that mean? It means that this warehouse 1 has to send all of its inventory out to these stores. Now, what that constraint should really say is really that shouldn't be an equal sign in that constraint. Let's go back. What that really should say, but I've written it this way for a reason, and that reason is just historically that's how people always do it, which is not a very good reason at all. But what this constraint really should say is that should really be less than or equals. What does that say? It says the warehouse cannot send more stuff than it has. The warehouse has 60 units of product available, and so it can't be sending 70 units, right? You couldn't do that. However, in business, it is perfectly fine if your warehouse is not sending all of its product away, right? There's just extra stuff lying around. In business, that's completely fine. In business or in the physical world, that's completely fine. The way this problem, which is a famous linear program, it's called the transportation problem. The way this problem has always been defined is that you have equal signs everywhere across here. Now, for this problem, it doesn't make a difference. It doesn't make a difference because, as I noted before, the total supply in the warehouses is 100 units, as is the total demand. So since you know the supply equals demand, you know that all these warehouses have to be sending out all of their supply. And so it doesn't actually affect the problem in any meaningful way to have equal signs here in these constraints. But if you're looking at that equal sign, scratching your head saying, well, wait a minute, why does the warehouse have to send out exactly this right amount of stuff? You're right to be thinking that way. That's a good intuition. It's perfectly fine to replace that equal sign with a greater than or equal sign. So that's where that first constraint comes from. The second constraint, not surprisingly, is just the same statement, but for the warehouse, the second warehouse, right? It says all the stuff leaving the second warehouse has to sum to 40. Excuse me. So what do we see for these three constraints down here? What does this one mean? 1, 1 plus 2, 1 is equal to 30. Again, I'm crowding up this slide too quickly. I'm so eager to draw things on it. So 1, 1 plus 2, 1 is equal to 30. Where does that one come from? What is 1, 1 plus 2, 1 in this picture over here? Let's erase some things. X1, 1 plus X2, 1 is this edge here plus this edge here. This is all the stuff that is entering store number 1, which has to be 30 units, as I've written there. So X1, 1 plus X2, 1 has to be equal to 30, as I've written there. And similarly, 1, 2 plus 2, 2 has to be equal to 40, that one there. That's this one over here. So 1, 2 plus 2, 2 has to be equal to 40. And 1, 3 plus 3, 3 has to be equal to 30. And that's it. That's the problem. That's the transportation problem. You can solve this linear program and you get the solution that I showed here a little while ago. So that's the transportation problem, and that's how that formulation and solution works. The last example we're going to do, we'll skip through all this stuff. This is just a formal description of the problem, which you can feel free to ignore. I just keep everything in there for completeness' sake. The last problem, this is a really neat one. Maximum flow. This picture I've been meaning to fix for a long time. I don't like this picture here because it shows both the input to the problem and the solution, and I don't like it when problems do that. I think you should have the problem in one piece and the solution in the other. So my apologies, but I hope I can make this clear enough. If you disregard the green and the magenta and the yellow stuff here, the colors in there, disregard that for the moment. That's the solution to the problem. And just look at this network underlying it here. Okay, you have this network and you have a start node, I'm calling that S, and an end node, which I'm calling T, that stands for terminal. And you've got these links in the network here that have numbers next to them. I've got a 6 here, and I've got a 1 there, and I've got a 3 there, and a 2, and a 7 like that. This is the black numbers that I'm looking at now, not the colored numbers. We're not going to look at the colored numbers just yet. These links here, we have these numbers on them, which we are calling capacities. Think of these links as being pipes, and think of these numbers, the black numbers, as being how much stuff that pipe can carry. And so this 3 here says this pipe is capable of carrying 3 units of whatever, water or whatever the heck is being transported in that pipe. And so the question we are going to ask is, what we want to do in this network is we want to send stuff from S to T along this network. We want to send like water from S to T along this network. And we want to send the largest amount we possibly can. We want to send as much as we possibly can from S to T. We want to know what's the largest amount that we can send, but you still have to obey these capacity constraints. So this link here is not allowed to send more than 3 units along it, and so on and so forth. Okay, so that's the idea. And the excuse me, the numbers here, or rather the colors here, actually turn out to be the optimal solution. And so the colors look like this. So you've got this green number here that you send 3 units along this path here, and you send 2 units along this magenta path here, and then you send 3 units along this yellow path down there like that. And sure enough, you could verify that we don't violate any capacity constraints anywhere. If you look at any of these edges, you can look at the amount of stuff that is moving along that edge and verify that the capacity constraint is not violated. So that's the idea there. And let's look at how you could solve that. Now this turns out to be a pretty tricky problem, or rather it is probably a very hard one to model. So let me erase all my markings here. One of the trickiest things about this problem is figuring out what your variables should be. In this problem here, it's tempting, and it is technically correct to say that you should have a variable for every path from the S to T. So S to A to B to T, you have a variable for that. And then S to A to D to T, there's a variable for that. And then S to C to D to T, there's a variable for that, and so on and so forth. You can do that. You can work that out. Theoretically, that works. That is a valid model for the problem. I won't expand on it and show you the entire thing because there is a problem with that model, which is that the number of variables that you need ends up getting very big very quickly. It scales exponentially, as we say, in terms of the size of the problem. So that would be a technically correct solution, but in terms of computing a solution, it wouldn't be a very good one. What actually makes the most sense for this problem is to have a variable for every one of these links here, every one of these little links along the network. And that's what I've got in the picture over here. So first of all, we have a maximization objective because we want to send as much flow as we can from S to T. And so we can say, well, how do we talk about the amount of stuff that's being sent from S to T? And you'd say, well, anything that's going from S to T, it has to be leaving from S, right? So let's just ask how much stuff is leaving S? Well, it's just all the stuff that's going from S to A plus the stuff that's going from S to C. And so therefore, my objective function is just x of S to A plus x of S to C. So all the stuff that is leaving S. Now let's look at my constraints. Where do these constraints come from? What does this one say? This says xSA is equal to x AB plus x, excuse me, sorry. XAB plus XAC plus XAD. What does that mean? Let's look back. What is XSA? Let's erase everything here. XSA is all the stuff that's coming along this edge like that. It's all the stuff that's coming in here. And XAB plus AC plus AD is this stuff here, right? It's this one and that one like that. And let me erase this lower left one, which is not part of this problem here. So what do we notice about the left-hand side of that equation versus the right-hand side? Let me erase that all again. And let's just highlight this entire line here. What do we notice about this one? You notice that the thing on the left is all the stuff that is entering A, and all the stuff on the right is the stuff that is leaving A. So what does this constraint tell us? It says anything that enters A has to leave A. That's what it means for something to be a flow through the network, right? If I'm sending water through pipes in a network, that water simply can't vanish somewhere. It has to go somewhere. So this is conservation of mass. You're saying anything that enters A has to leave it. And in fact, I have one constraint for every one of these nodes here, right? If you just go down the list, I've got this one here, XAB is equal to BD plus BT. And in fact, if you just go through all of these constraints here, I've just got constraints that say anything that comes in has to leave. You'll notice I don't have a constraint for S or a constraint for T because there's nothing entering S and there's nothing leaving T, right? Because you're trying to send stuff from S to T, and so we don't have to worry about this conservation of mass in that case. So those are all the real constraints here. The remaining constraints are really easy. This stuff here, these are just the capacity constraints on those edges. This says S to A is less than or equal to 6. That's just showing, excuse me, wrong way, let's skip back to. That's just saying that you're not allowed to send more than 6 units from S to A, which is this number 6 right there. And those are just capacity constraints on all of those units there. So they're not very interesting at all. So that's called the maximum flow problem. It's another very famous linear program that is, I think, probably the least intuitive of the problems that we've looked at so far. But now that you've seen it, it tends to be one of these things that is very hard to forget, which is kind of nice. Let's talk about standard form of a linear program. We say that a linear program is in standard form if it has the following 3 properties. Number 1, your objective function says minimize. Number 2, all of your constraints have equal signs here. And number 3, your variables all are constrained to be non-negative. If you like linear algebra, you could write it like this. It's just minimize C transpose X, AX is equal to B, and X is non-negative. So those 3 conditions: minimization objective, all your constraints have equal signs, and all of your variables are non-negative. That's called a standard form linear program. In fact, if you look back, there was exactly one example of a standard form linear program that we've already done. That was the transportation problem example. I'll skip back there if I can make it. The transportation problem, what was the one I wanted to look at here? I want to show you the smaller one, which is the 2x3. There we go. No, one more. There you go. You can look at this linear program, and indeed it has these conditions. It has a minimization objective, it has equal signs for all the constraints, and you have non-negativity for your variables. So the transportation problem is the one problem you've seen so far that happens to be in standard form. Okay, so why am I talking about standard form? Why is this somehow a special thing? Well, we can ask the question here, is it always possible to take a linear program and transform it into one that is in standard form? Okay, so I've shown you a lot of problems that had maximization objectives instead. Some problems are allowed to have negative variables. Some problems have constraints that have inequalities in them. And we'll just ask the question, okay, is it true? Can we take, if I give you a linear program, is there a way for you to manipulate it and transform it and add variables in and add constraints and do all kinds of manipulations to transform any linear program into standard form? If the answer is yes, we're pretty happy about that, because then it means that from a technological standpoint, if we're creating algorithms that solve linear programs, we're perfectly fine to just focus on standard form problems like the one you see here, right? It says you don't need to have, if you can do this, it would make you pretty happy, because you'd say, well, okay, I don't need to worry about, like, this is a solver that only works for maximization linear programs, or this is a solver that only works for inequality constraints that go that way, or this kind of thing. So we'd be happy if that were true. So we could pause the video and take a poll there. Yes or no, do you think it's always possible to do that? The answer is yes, you absolutely can. You can always take any linear program that I give you, and you can add variables, add constraints, play with things to transform it into an equivalent linear program that is in standard form. Let's start with the easy one, the minimization objective. So I've got a standard form requires that your objective function is minimize. And so we'd say, well, what if I have a maximize problem? What if I have a maximization objective? I'd say that's actually fine, because if I say maximize C transpose X, that's the same as minimizing negative C transpose X. So if I wanted to maximize x1 plus x2, that's the same thing as minimizing negative x1 minus x2. So turning a maximize problem into a minimize problem is completely trivial. If you need to go from one to the other, you just multiply the objective function by -1. So at least we've satisfied that the difference between a minimization linear program and a maximization linear program is sort of immaterial. It really doesn't have any, there's no real material distinction between the two. Okay, so that's an easy one. But how about linear inequalities? Let's look at this linear program here. This thing almost looks like standard form. You've got a minimization objective. You've got all your variables are non-negative. And almost all of your constraints have equal signs except this one. You've got one less than or equals in it. So everything is in standard form except you've got one annoying constraint like that. So you'd say, okay, how do I turn that less than or equals sign into an equals sign? It's a really, both of the tricks I'm going to show you here, they're the kinds of things that you would feel like would not be allowed in a linear algebra class. It feels like the kind of thing where you want it to be true and you just know the instructor is going to tell you it's not. They do work here, and the trick is the following. You say, if I tell you that this thing here, this expression, is less than or equal to q, that is the same thing as me saying that that expression there plus a new variable which I'm calling xn plus 1 is equal to q, where xn plus 1 is non-negative. Okay, I'll say that again. Well, actually, I'll do it this way. What I want to get across here is that this statement here is identical to this statement down here, provided that this new variable we introduced, which I'm calling xn plus 1, is non-negative. Right? If I say a is less than b, then it means a plus x is equal to b, with x is non-negative. In fact, let me write that down. But I'll say with x's instead, because that's what we're going with. Let me do something really concrete. If I say x1 plus x2 is less than or equal to 17, that is the same thing as me saying x1 plus x2 plus x3 is equal to 17, and x3 is greater than or equal to 0. Right? Those are manifestly the same thing. I've just introduced an extra variable, and I've sort of shifted the inequality into that. We call these new variables slack variables. And so if you give me a linear program with a bunch of inequality constraints, I can transform all of those into constraints with equal signs just by introducing a new slack variable at each one of them using exactly the trick I showed you here. So that's not very difficult. And this is now what the revised standard form linear program would look like with that transformation there. So you now have this x plus 1 in there, and now I've got equal signs everywhere and non-negativity everywhere. So that's no problem. Now, free variables are even more ridiculous. It's an even sillier trick. This is a linear program here that almost looks like standard form again, except that xn is actually does not have a sign constraint. So xn is allowed to be negative. So let's say, okay, well, you've got a variable that's allowed to be negative now. So how do you work with that? Once again, it's actually pretty simple, but now you introduce two new variables, and those two new variables are done as follows. What you do is you say, okay, every place where I have an xn, so xn, again, this is the variable that is allowed to be negative, every place where xn appears, I'm just going to like scribble that out. I'm going to do a control F or a, find and replace. I'm going to erase that, and instead I'm going to write xn plus 1 minus xn plus 2. So I'm introducing two new variables, and I'm saying xn is no longer going to live in this linear program. We're going to get rid of that, and we're going to replace it as one variable minus another variable. Now, what does this trick accomplish for me? Well, I'm allowed to assume that both of these new variables I'm introducing, xn plus 1 and n plus 2, I'm allowed to say that they are both non-negative. That's perfectly fine because xn is being replaced by their difference. And the two non-negative things, their difference is allowed to be negative. And so by replacing xn with this difference now, I'm allowing for the possibility of a negative value. So the transformed LP now looks like this. xn no longer lives anywhere here. I just have xn plus 1 minus xn plus 2 everywhere throughout. And if you want, you can expand this out just to be sort of pedantic and get the standard form LP there. So those are the three tricks that you've now learned that tell you how to transform any linear program into standard form. For turning a maximization objective into minimize, you multiply the objective by -1. For turning an inequality constraint into an equal sign, you introduce these slack variables. For turning a variable that's allowed to be negative into one that, for getting rid of a variable that is allowed to be negative, you write that free variable as the difference of two non-negative variables, and you work with that. This is a good set of problems to practice. These are great exam problems, and so these are rules you should know very well, and we'll go through a lot of that in class. Another trick that is pretty neat is that, in fact, there are some problems that are not linear explicitly, but which you can still solve using linear programming. This example here looks almost like a linear program, except it has an absolute value term in it, right? There's an absolute value term of x2 there in the middle. And you could say, okay, how could I handle this problem here? How could I solve this problem? If I know how to solve linear programs, how could I solve this thing? It's a trick that works like this. The first thing you do, I'll do something that is totally of no consequence. I'm going to say, well, instead of absolute value of x2, I'm just going to write the letter t. I'm going to introduce a new variable there, t. And I'll say, oh, by the way, t is equal to the absolute value of x2. A useless change, right? I haven't done anything there, right? There's no content to that. I've just taken a t and I've set that equal to this term that's bothering me. Okay, but what this allows me to do is the following. I could say, okay, t in this thing appears in two places, right? The two places I've just underlined, up here and down there. Now, this is a minimization problem, which means that I want t to be small, right? It's a minimization problem, and t appears like that, so I want t to be small. I also want 3x1 to be small, and I also want 4x3 to be small, but we're not going to touch those right now. What I want to point out here is that what I'm allowed to do without changing anything of any substance is I can take this equal sign, where I said t is equal to absolute value of x2, and I can replace it with a greater than or equal sign like that. Okay, why am I allowed to do that? I'm allowed to do that because I have t appearing in two places, here and here, and I have a minimization problem. So let's suppose that t was actually strictly greater than the absolute value of x2. So suppose this constraint was not tight, so there was slack there. Well, what I want to do, I'd want to make t get smaller because I have a minimization problem. So because I have a minimization in the objective here, I want t to get small, which means that whatever solution I have, I'm going to make t get as small as I can before it hits any constraints. But t only appears in this constraint down here, and therefore we know that when we solve the problem optimally, this value for t will actually be equal to the absolute value of x2. So we know that's true. So in fact, I didn't change anything, or I'm claiming that the solution did not change when I went from the problem with an equal sign, this one back here, with an equal sign, to the problem that has an inequality. You could say, okay, All right, I believe you on that. You did two things so far. You had an absolute value term, you introduced this variable t for some reason, and then you set t equal to that absolute value. And then you claim that you can replace the equal sign with this inequality as you just did. You can say, okay, I believe it. You've still got an absolute value sign there. How do you get rid of this thing and solve it as a linear program? Well, if I say t is greater than or equal to the absolute value of x2, that is the same thing as me saying that t is greater than or equal to x2 and t is greater than or equal to minus x2. All right, we could draw a picture to verify that, and I think I'll do that now. So where does that come from? It's going to be kind of small, sorry about that. But I've said t, so what am I going to do? I'm going to put t put some axes there. And I've said t is greater than or equal to, so t is going to be there. And then x2 is going to be on the horizontal axis like this. And I've said t is greater than or equal to absolute value of x2, which means it lies, above this part there, like that. And what do these constraints say? The first constraint says t is greater than or equal to x2, which means you have to lie above this line, like that. In fact, here's what I should have done. The first constraint says you have to lie above this line, t is greater than or equal to x2, and then this other line here is t is greater than or equal to minus x2, which I'll do with hatching like that. And so you can just verify with drawing a picture that in fact that those conditions are equivalent. Okay, and what's nice about this one is I've now finally gotten rid of that absolute value term, as you can see there. This also works even when the absolute value term appears in a more complex way. So this example here, I've also got an absolute value term that has a bunch of other stuff going on inside it. And so let's see, where does that get changed? So I replaced the x1 absolute value with something called s, and I replaced this absolute value term there with something I'm calling t. And then so what happened with s is the same setup that we had before. S is greater than or equal to x1, and it's greater than or equal to minus x1. And then t is greater than or equal to this quantity here, and also the negative of this quantity over here, to x2 minus x3, I think. So, so that is how you minimize absolute values. We can take this concept one step further as follows. Let's suppose I have a problem where my objective function is actually, let's say it is the maximum of 3 expressions here. A lot of people get thrown off by this, so I have to go very, very carefully. Let's say you have an objective function like this one here, f of x1 comma x2, and it is the maximum of these 3 things. Okay, this is what you'd call a piecewise linear function, and I've sketched it here with this plot. You can see it's like 3 sort of linear pieces that are sort of coming together. And what this just means you take any x1 and x2, and you evaluate this expression, you evaluate this expression, and you evaluate this one. And because we have the word max there, you take the largest of those 3, and that is the output of the function. This is like when people are describing like how much they charge you for something. They'll say, like if you're, I don't know, getting a warranty for a car, they'll say, well, it's 5 years or 75,000 miles, whichever one comes first. It's like that. You're saying, well, it's whichever of these various expressions is the largest, or whichever one comes first, is how we'd say it in the car warranty example there. So let's deal with functions like that. Okay, this is where you have a function, and that function is itself like the largest of a bunch of linear components. It sounds harder than it is. Okay, let's ask if we can minimize this function if we have linear constraints on these variables here. So we'll take this function here. F of x1 and x2 is the largest of these 3 things. And let's say, okay, can we minimize this thing subject to, garden variety linear constraints on these variables? Yes, you can. And all you have to do is the exact same trick that I described before for absolute values. And we'll see how that carries out. So this expression here, it's the maximum of these 3 terms. Again, you just write the letter t. That's going to be our new variable t. And what has to be true? T is going to represent whichever one of these 3 terms is the largest. Let me highlight that correctly. Move it over. it has to represent which of these three terms is the largest. So what has to be true about t? Well, we're minimizing t, and t is going to represent whichever of these three expressions is biggest. So t has to be greater than or equal to the first expression, and it has to be greater than or equal to the second expression, and it has to be greater than or equal to the third expression. So it has to be at least as big as all of these three expressions. And since we're minimizing t, we're going to make it as small as we can get it, while still being at least as big as these three terms, which means that at the optimal solution, it will be equal to the value of the largest one. Again, it looks harder than it is. You work through a couple of examples. You watch me do a few of these in the discussion, and it's not very challenging or intimidating at all. You may remember the method of least squares, aka the line of best fit, from maybe a statistics class or calculus. What does that mean? It's a problem where you've got some data points. You can ignore the lines here for a minute. I just want to get the idea across. You've got some data points, as I've got there, and you're looking for a line that sort of approximates them to the best extent possible. Let me erase all that now so I don't forget it later. So you could ask the question of, how do you, well, you've already learned how to do this using the so-called method of least squares. And what that was based on, since you've probably forgotten, is the following. The way you would have done that in calculus, where you learned that you minimize things by setting derivatives to 0, is you'd say, well, if I've got data in the plane, I've got a bunch of x's and y's, these are my data points, I would say I want to fit a line of the form y equals ax plus b. And I'd want to say I want to fit a line that minimizes the error. So what is the error? For each one of these data points, I've got a y, and then I've got an ax plus b. And I'd like that error to be as small as possible. When you did this in calculus, what you would have done is you would have taken the square of all of these errors. You'd say, let's take the gap between all of these things, and let's square those errors and sum them all up. Why did you square them? Your calc teacher probably told you that you did that because the squaring function is differentiable, and we like setting things with derivatives to 0, and we can solve things that way. And you probably did that, and you derived the normal equations, and you got the expressions for these slope and intercept and all that. And everything worked out just fine. Okay, that's a perfectly fine way to solve the problem. It is nonlinear, so nothing I've told you so far is going to help you with that. It's nonlinear because of that squared term there, right? We haven't done any squares of any things here. That's quadratic. That's not linear. So nothing I've told you here would apply. But we could try our own approach to this. We could say, let's minimize the largest error. Okay, let's take, instead of minimizing the sum of the squares of the errors, instead, let's minimize the largest error. So in other words, that would be the maximum over all of these, like that. The maximum of all these absolute values. And the absolute value is what you see here. Minimize z, subject to z is greater than or equal to each one of these error terms individually, positive and negative, and it would look like that. So what does that mean? If you look at this diagram here, I've got some data points, as I described a moment ago, and I've got two lines that I've drawn. The lower one in orange represents the traditional line of best fit, the least squares best fit. And then the yellow one represents the one using this linear program where you're minimizing the maximum error. And you can see that the maximum error for that least squares fit is this thing over here, which is pretty big, whereas the maximum error for the line we computed using the linear program has a maximum error that's this thing, and that thing, and that thing. So the maximum error is smaller. The real point I want to convey with this example is just that you can use linear programming to perform your own kind of linear regression, that it is the concept does apply, although you have to think of things in a linear fashion rather than through least squares and squaring these errors and setting derivatives to 0. But the concept does apply.